Schrödinger's cat is a thought experiment proposed by the Austrian physicist Erwin Schrödinger in 1935, challenging our understanding of reality and the fundamental principles of quantum mechanics. It involves a hypothetical cat placed inside a sealed box with a mechanism that could potentially kill the cat, depending on the decay of a radioactive atom. Until the box is opened and observed, the cat is considered to be both dead and alive simultaneously, exemplifying the principle of superposition in quantum theory. This dual-state phenomenon illustrates how objects can exist in multiple states at once, only collapsing into a single definite state upon measurement or observation. Schrödinger's cat serves as a bridge between the visible, macroscopic world and the peculiar, often counterintuitive quantum realm, inviting us to rethink and question our understanding of the universe and the nature of reality itself. It remains a crucial and thought-provoking concept in both science and philosophy, sparking debates and discussions to this day. Modern quantum experiments continue to explore and expand upon Schrödinger's ideas, pushing the boundaries of what we know about the quantum world. The thought experiment has fostered an interdisciplinary dialogue, bringing together physicists, philosophers, and even laypeople to ponder the mysteries of existence. Schrödinger's legacy endures, reminding us of the profound and often perplexing nature of the universe we inhabit. Imagine placing a cat inside a box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. This setup is not just any ordinary box, it is a thought experiment designed to challenge our understanding of quantum mechanics and classical physics. If the atom decays, the Geiger counter triggers the hammer to break the vial, releasing the poison and killing the cat. This chain reaction is instantaneous and irreversible, highlighting the delicate balance of life and death within the box. If the atom does not decay, the cat remains alive. The cat's fate hinges entirely on the behavior of a single atomic particle, making it a prisoner of quantum uncertainty. The setup is sealed off from any external interference, encapsulating the cat's fate within the quantum realm. This isolation ensures that no outside factors can influence the outcome, making the experiment a pure demonstration of quantum principles. In the quantum world, particles like atoms exist in a state of superposition, simultaneously in multiple states until they are observed. This means that the atom can be both decayed and not decayed at the same time, a concept that defies our everyday experiences. Thus, if the atom state is both decayed and not decayed, then the cat, by extension, is both alive and dead. This paradoxical situation is at the heart of the thought experiment, challenging our understanding of reality. This superposition persists until an observer opens the box and checks on the cat. The act of observation collapses the superposition, forcing the atom, and consequently the cat, into one definite state. The experiment illustrates a fundamental difference between the quantum and classical worlds. In the classical world, objects have definite states, but in the quantum world, reality is much more fluid and uncertain, governed by probabilities and possibilities. Quantum mechanics deals with the behavior of particles at the smallest scales. These particles include electrons, photons, and other subatomic entities that make up the fabric of our universe. At this level, the rules of classical physics no longer apply, and we enter a realm of probabilities and uncertainties. The principle of superposition states that particles can exist in multiple states at the same time until they are observed. This means that a particle can be in a state of flux, embodying several possibilities all at once, a concept that challenges our traditional understanding of reality. Imagine a coin spinning in the air. While it spins, it's both heads and tails. This analogy helps us grasp the idea of superposition, where a particle is in a combination of all possible states. It's only when the coin lands, akin to being observed, that it becomes either heads or tails. This act of observation collapses the superposition into a single state, a phenomenon known as wave function collapse. Particles can be in multiple places or states simultaneously. A particle can travel through multiple paths or exist in different states all at the same time. This is not just theoretical. Experiments have shown particles behaving in this manner. This defies our everyday experiences, but is normal in the quantum world. The quantum realm operates under its own set of rules, which often seem counterintuitive to us. Understanding superposition helps physicists predict and manipulate the behavior of quantum systems. By mastering these principles, scientists can develop new technologies and gain deeper insights into the nature of reality. It's the foundation for technologies like quantum computing, where bits can be both 0 and 1 simultaneously. This duality allows quantum computers to perform complex calculations at unprecedented speeds, potentially revolutionizing fields such as cryptography, medicine, and artificial intelligence. Schrödinger's cat, being both dead and alive, illustrates the principle of superposition. Until the box is opened, the cat's fate is a cloud of possibilities rather than a definite reality. This dual possibility exists as a real consequence of the quantum laws that govern subatomic particles. The cat's dual state challenges our classical intuition about how things should work. In the world we perceive, dead and alive are mutually exclusive states. However, quantum mechanics reveals a layer of reality where these rules do not apply. This has profound implications for our understanding of reality itself. It opens up a universe where the act of measurement determines the state of what's being measured. Quantum uncertainty is another key concept illustrated by Schrödinger's cat. In classical physics, we can predict the outcome of a system with great accuracy if we know the initial conditions. However, in quantum mechanics, there is an inherent uncertainty that cannot be eliminated. This is encapsulated in Heisenberg's uncertainty principle. In the context of the cat, the uncertainty lies in the state of the atom, whether it has decayed or not. This uncertainty extends to the life status of the cat. It's not that we don't know whether the cat is alive or dead, rather, it is both alive and dead until we check. This fundamental uncertainty drives much of the research in physics today. Schrödinger's cat has real-world implications across various fields of science. By demonstrating superposition, it provides a foundational understanding for quantum computing. In these machines, bits of information can exist in multiple states simultaneously, vastly increasing computing power. The experiment also impacts quantum cryptography, creating secure communication systems. In medicine, quantum mechanics enables high-precision imaging techniques. The thought experiment challenges and expands our philosophical understanding of reality. It forces us to reconsider our notions of causality, existence, and the structure of reality. Schrödinger's cat remains a compelling example of the strange, counterintuitive nature of quantum mechanics. In quantum mechanics, the observer influences the outcome of events. Schrödinger's cat underscores this point. The state of the cat is determined when it is observed. This is known as the collapse of the wave function. The observer effect suggests that reality does not exist in a definite state until it is measured. This concept has profound implications for our understanding of causality and reality. It suggests a universe that is interactive at the most fundamental levels. The observer effect is pivotal in experiments involving quantum entanglement. Understanding the role of the observer in quantum mechanics is essential for exploring the quantum world. The transition from classical to quantum mechanics is one of the most fascinating shifts in science. Classical physics does not account for behaviors observed at microscopic levels. Schrödinger's cat serves as a bridge illustrating the complexity of quantum phenomena. In classical physics, objects have definite positions and states. Quantum mechanics introduces a realm where certainties dissolve. This bridging has practical applications such as in semiconductor technology. Understanding quantum properties has led to faster, smaller, and more efficient electronic devices. Schrödinger's cat offers a glimpse into the complex transition between classical and quantum worlds. Quantum superposition has practical applications revolutionizing technology. Quantum computing uses qubits to perform multiple calculations at once. This allows quantum computers to solve problems at speeds unattainable by classical computers. Quantum superposition is at the core of quantum sensors, used in various applications. These sensors measure physical quantities with extreme precision. Quantum networks involve transmitting information through entangled quantum states. This technology could lead to unbreakably secure communication systems. The principles underlying Schrödinger's cat are having real, tangible impacts on technology and innovation. Schrödinger's cat poses profound philosophical questions about reality, observation, and knowledge. It challenges the classical notion that objects have an independent reality. Instead, it suggests a reality in flux until measured or observed. This has implications for the philosophy of science and the nature of knowledge. The thought experiment underscores the limitations of human intuition. It invites us to consider the complexity and mystery of the universe. These philosophical explorations influence how we approach complex problems. Schrödinger's cat challenges us to rethink our assumptions and expand our understanding of the universe. Schrödinger's cat is a symbol of the mysterious nature of quantum mechanics. It has played a crucial role in the development of quantum theory. The experiment's impact extends beyond physics, influencing various fields. It challenges us to rethink our notions of reality, observation, and knowledge. Schrödinger's cat remains a fundamental concept in exploring the quantum world. Its legacy is a testament to the power of thought experiments in advancing knowledge. Schrödinger's cat illuminates the peculiarities of quantum mechanics. It enriches our intellectual and philosophical landscape, proving that great discoveries come from asking, what if?